Yes, welcome to this session. See the question number 9. The trigger circuit of a thyristor is shown in figure. The thyristor requires a gate current of 10 milliampere. For guaranteed turn on, the value of R required for thyristor to turn on reliably under all conditions of VB variation. Okay. For reliable turn on of thyristor, the thyristor requires a gate current of how much? 10 milliampere. Yes. That means whatever the voltage we are applying, that must drive 10 milliampere. Minimum is 10 milliamp. Reliably, minimum is 10 ampere. Above that also we can apply. Then SCR will be turned on. But below 10 milliampere, that SCR will not be turned on. Okay. That means whatever the voltage we are applying, that voltage must be 10 milliampere with a given resistance. For all variations of VB means what the solution for this problem is? VB is given as 12 plus or minus 4 volts now. Okay. This means it may be 8 volts or it may be a 16 volts. One way of solving this problem is check the options. According to options, we can solve how much resistance we can connect for reliable turn on. For reliable turn on means whatever the resistance that should be connected, that must drive 10 milliampere or above that. If it is drive below that, then it is not possible. For example, you take 8 volts connecting. We are connected 8 volts. We are connected 8 volts and you taken 10,000 ohms. 8 volts, 10,000 ohms. 8 volts, 10,000 ohms means, then what is the current? 8 volts, 10,000. For example, we are checking for 10,000 ohms. Check for 10,000 ohms. Okay. First condition is 8 volts. For 8 volts, 10,000 ohms means, what is the gate current? 8 by 10,000. That is 0.8 milliamperes. For 12 volts means, what is IC? 12 by 10,000. This how much you can get? 1.2 milliamperes. This is meaningless. Using, if you connect 10,000 ohms, that SCR will not turn on because these two currents are less than 10 milliampere. Check for 1200 ohms. If you take 1200 ohms. If you take 1200 ohms means, if for 8 volts variation, 8 volts variation means IC equal to 8 by 1200 ohms. This is less than 10 milliampere. Okay. Then for 12 volts means what is IC? 12 by 1200. Then how much we get? This we can get. How much we can get? 12 by 1200. This also less than 10 milliampere na? 12 by 1200. 1 into 10 or it is equal to 12 milliampere. But for 12 volts it will on. But for 8 volts it is not on. Na? That's why it is not a 1200 ohms also. For all VB variations, for 8 volts also it must be on. 12 volts must be it must be on. Like that we can select the resistance. Understood? Next, for example, you selected 1600 ohms. If you selected 1600 ohms means for 1600 ohms, if you selected 1600 ohms, then for 8 volts, 8 by 1600, this is less than 10 milliampere. For 12 volts, if you select this one, 12 by 1600, this also less than 10 milliampere. That's why it is not also important combination. Then you take 800 ohms. If you take 800 ohms means, then how you write 8 volts, 8 by 800. Then how much you get? 10 milliampere. For 12 volts, you select 12 by 800. that is greater than 10 milliampere. Then this is important. That's which is the best option? 800. That is one way to answer. The another way you write directly means, directly also you write the formula like this, directly. You take minimum voltage. For minimum voltage, for 8 volts, for minimum voltage, this VB variation, for minimum of VB variation, the resistance which gives 10 milliampere or greater than 10 milliampere, that resistance is the connected for reliable turn on. That is the resistance connected for reliable turn on. What I am telling, instead of checking all these options like this, do like this. Select the minimum variation of VB, corresponding to that VB, the resistance which gives 10 milliampere or greater than 10 milliampere. That resistance is the resistance required for reliable turn on. Understood? Now, directly means how to write means, what is the minimum voltage? VB minima is how much? 8 volts. Minimum variation of VB is 8 volts. Then we know that what is you want to find R now? R equal to VB minima by I. Okay. What is VB minima? 8. What is I? 10 milliampere. 10 milliampere. Then what the resistance we can connect? The resistance equal to 800 ohms. Like this directly also we can solve. The total VB variations, this is VB variation. Select minimum voltage. From that minimum voltage, you already given, current is given, you calculate resistance. That is the resistance must be connected for reliable turn on. Remaining resistances will not give the reliable turn. Clear? Instead of checking all these, then go for that. Like that also you can solve. No doubt. Then what is the option for this one? Answer for 9th question is option D. Number 10. Yes. A thyristor data sheet gives 1.5 volts and 100 milliampere as the minimum value of gate trigger voltage and gate trigger current respectively. A resistor of 20 ohms is connected across gate cathode terminals. For a trigger supply voltage of 8 volts, calculate or compute the value of resistance that should be connected in series with gate circuit to ensure turn on of the device. Yes. A thyristor data sheet gives 1.5 volts and 100 milliamperes as the minimum value of gate trigger voltage and gate trigger current. Then what the solution for this problem is? Vg is given as 1.5 volts. Ig is given as how much? 100 milliamperes as the gate trigger voltage and gate trigger current. A resistance of 20 ohms is connected across gate cathode terminal. Across gate cathode terminal, Rg is 20 ohms, it is connected. Rg is 20 ohms is connected. Okay. For trigger supply voltage is how much it is given? 8 volts. Then calculate gate to cathode resistance. Calculate gate source resistance for reliable turn on. Compute the value of resistance that should be connected in series with gate circuit. Okay. Then according to given data, you draw the circuit, gate trigger circuit. This is given like this. At the gate 2, the source resistance is Rs. Gate supply voltage is 8 volts, it is given. Yes. Gate to cathode resistance is given as how much it is given? Yes, 20 ohms it is connected, and let this is IC, let this is VC, let this is IS. Okay. Now from this you want to calculate RS. You want to calculate RS means I want to define IS. Then what is IS equal to, you tell me? IZ plus, let this current is, if any resistance is connected across gate cathode terminal, I told that what the resistance we can take, that resistance is taken as a IR. Okay. Then what is the source current? IS equal to, what is IZ is given? 100 milliampere. 100 into 10 to the power of minus 3. Okay. What is IR, you tell me? VZ. VZ is 1.5. 1.5 by 20. Then how much IS we can get? This is 0.1 plus. This is how much we can get? S. This is 1.5 means 0.075 now. Okay. Then 0.175 amperes. IS equal to 0.175 amperes. Then we know that apply the KVL for this loop. If the KVL is applied, then 8 volts equal to, apply the KVL for this one, 8 volts equal to IS into RS na, IS into RS plus, this is VC. Okay. Then from this, what is RS equal to? 8 minus VZ by IS na. Then RS equal to 8 minus VZ 1.5, IS 0.175 amperes. Then you can get RS equal to 37.14 ohms. This is the resistance we can connect in series with gate circuit. In series with gate circuit, how much resistance we can connect means this RS equal to 37.14 ohms we can connect. 11th question. Yes. The trigger circuit of a thyristor has a source voltage of 15 volts and the load line has a slope of minus 120 volts per ampere. The minimum gate current to turn on the SCR is 25 milliamperes. Okay. Compute the first one is, that is A, source resistance required in the gate circuit. Second one, that is B, the trigger voltage and trigger current for an average gate power dissipation of 0.4 watts. Okay. Trigger voltage and trigger current for an average gate power dissipation of 0.4 watts. Okay. The trigger circuit of a thyristor has a source voltage of 15 volts. Then what the solution for this problem is? The trigger circuit of a thyristor has a source voltage of 15 volts. What is Vs? It is given 15 volts is given. Okay. Yes. The slope of the load line equal to slope of the load line is how much? Minus 120 volts per ampere. Slope of the load line is minus 120 volts per ampere. Minimum gate current to turn on the SCR is IZ minima. The minimum gate current to turn on the SCR is 25 milliamperes. First one is A, source resistance required in the gate circuit. Source resistance equal to source resistance required in the gate circuit. Source resistance required in the gate circuit. In the gate circuit. We know that slope of the load line equal to slope of the load line in the gate characteristics. Slope of the load line indicates which resistance? Indicates gate source resistance. Gate source resistance. Slope of the load line indicates gate source resistance. In the given problem, slope of the load line is minus 120 volts per ampere. Therefore, gate source resistance RS equal to 120 ohms. This is the first question answer. Slope of the load line indicates gate source resistance. What the slope of the load line is given? Minus 120 volts per ampere. Therefore, source resistance, gate source resistance is 120 ohms. What is the second one? Concentrate on second question. B. The trigger voltage and trigger current for average gate power dissipation of 0.4 watts. If VG and IZ equal to 0.4 watts. If VG and IZ equal to 0.4 watts. Okay. VG and IZ equal to 0.4 watts. Then you calculate what is VG, what is IZ. Okay. Calculate what is VG and what is IZ. Gate trigger voltage and trigger current. We know that Vs equal to Vg plus Iz into Rs. What is Vs? Vs is how much it is given. Gate supply voltage is given is 15 volts now. This is 15. This is, we know that Vg plus Iz is how much? Iz is given as you want to calculate Vg and Ic. Rs you calculated na. This is 120 Ic. 120 Ic. Now let this is equation 1 and this is equation 2. Then solve equation 1 and 2. Solve equation 1 and 2. Two equations, two unknowns. Then we can get what is Vg and what we can get what is Ic. Two equations and two unknowns. We can get what is Vg and what is Ic. Okay. Then from this one, from equation 1, tell me what is Vg equal to? Vg equal to 0.4 by Ic. Okay. Then you substitute here 15 equal to Vg plus Vg is how much? 0.4 by Iz plus 120 Ic. Okay. Then from this one, 120 Iz square minus 15 Iz plus 0.4 equal to 0. Solve this quadratic equation. By solving this quadratic equation, we can get Iz equal to 38.56 milliampere, and you also get another one is quadratic equation 86.44 milliamperes or 86.4 milliamperes. Now if Iz equal to 38.56 milliampere, then what is Iz? Iz equal to, then what is Vg? Calculate na. Then Vg equal to, what is Vg? 0.4 by Iz. This we can get 10.37 volts. We get 10.37 volts. This is one calculation. This is Iz, this is Vc. Similarly, if Iz equal to 86.4 milliamperes, then what is Vg? Vg equal to 0.4 by 86.4 into 10 power minus 3. Then we can get 4.627 volts. Then which is the best selection means? We know that the selection of IC must be, which reduces the turn on time, that IC must be, you can select. We know that if the gate current is increases, then turn on time will be reduces now. Then which is the best selection? This IC equal to 86.4 milliampere, this VC equal to 4.627 volts. This is the best selection. But again you have doubt, sir, if the gate current is increases, then gate will be damaged. But don't think like this. Whatever the gate current we are calculated, this one, this gate current is calculated according to allowable gate power dissipation only. Yes or no? We are calculated this VC and IC is according to 0.4 watt. This is average gate power dissipation only. According to average gate power dissipation only, we are calculated IC. Here we are getting two ICs. One IC is 38.56 milliampere. Another IC is 86.4 milliampere. Both we can apply. Understood or not? But these are not damaging gate currents. These gate currents cannot damage the SCR. Why it cannot damage the SCR? Because these are calculated according to average gate power dissipation only. But now I want to select which current you want to select. That is, you have the doubt. Okay, is it 38.56 you want to select or 86.4 milliampere you select? The best selection is 86.4 milliamperes, because if you apply the high gate current, that will reduce the turn on time. That's why corresponding to IC equal to 86.4 milliamperes, how much gate voltage we are getting? 4.627 volts we are getting. 4.627 volts we are getting now. That's the reason why this is the gate trigger current and gate trigger voltages. Clear? The problem number A is you calculate gate source resistance. How to calculate gate source resistance means, because slope of the load line is given. Slope of the load line directly indicates which resistance? Gate source resistance. Then you calculate gate trigger voltage and gate trigger current for a given average gate power dissipation. That is 0.4 watts. If average gate power dissipation is given, then how to solve? That you can write. Yes, concentrate. Hold on. See the question number 12. Yes, concentrate. Question number 12. Okay. What is the solution for this problem? Yes. For an SCR, maximum gate power dissipation is 50 watts and average gate power dissipation is 5 watts. Compute the Mark II space ratio. Yes, simple question. For an SCR, maximum gate power dissipation is 50 watts. That is, PG maxima is given. Maximum gate power dissipation. How much it is given? 50 watts. 50. Okay. Average gate power dissipation is given. Average gate power dissipation is given. PGAV. How much it is given? 5 watts. Okay. Then we calculate Mark II space ratio. Calculate Mark II space ratio. Yes. Tell. How to calculate Mark II space ratio? We know that Mark II space ratio is nothing but a mark by space. Mark is nothing but a on time. Space is nothing but a off time. This formula is given. On time by off time is defined as delta by 1 minus delta. We know this condition in a pulse triggering of SCRs, average gate power dissipation equal to PGM into delta, maximum gate power dissipation into delta in a pulse triggering SCRs. Then delta equal to PGAV by PGM, average gate power dissipation by maximum gate power dissipation. PCAV by PCM. What is the average gate power dissipation? 5 watts. Okay. What is the maximum gate power dissipation is given? 50 watts. Maximum gate power dissipation is given as 50 watts. Then what is delta equal to? 1 by 10. Then you calculate mark to space ratio. Na? Then mark by space equal to. Mark by space equal to. That is delta by 1 minus delta. Delta is calculated 1 by 10. 1 minus 1 by 10. Then how much you get? 1 by 9. Simple problem. Concentrate. Given that maximum gate power dissipation and average gate power dissipation, calculate mark to space ratio. Mark to space ratio is nothing but a on time by off time. On time is delta t, off time is 1 minus delta into t, then tt cancel, delta by 1 minus delta. Then you know this relation, PGAV equal to PGM into delta, that delta equal to PGAV by PGM, that 5 by 50, that is 1 by 10, then mark to space ratio equal to 1 by 9. Yes, clear? Okay. This one model of question, how to calculate mark to space ratio. Okay, this is classroom workbook question based on topic 2 that you concentrated. Okay, I solved nearly 12 number of questions that you clear, get idea how you are applying the formulas to solve these problems. Okay, now based on this topic itself, this is not given in classroom workbook. This you note down this example. I'm not giving question number, just I'm giving as one example based on this model only. For example, if it is given like this, then how to solve the problem? Okay, it is not mentioned in classroom workbook. This I am given as one example. Clear? For example, if the question is framed like this. For a DC triggering, for example, if the DC triggering is used, for a DC triggering of SCR, this you remember as a note, for DC triggering of SCR, the average gate power loss is, the average gate power loss is 20 watts. The average gate power loss is 20 watts. If the pulse triggering is used, if the pulse triggering is applied with a duty cycle of 0.2, then the average gate power loss is dash. If the pulse triggering is applied, if the pulse triggering is applied, if the pulse triggering is applied, okay, if the pulse triggering is applied, if the pulse triggering is applied, if the pulse triggering is applied with a duty cycle of 0.2, with a duty cycle of 0.2, with a duty cycle of 0.2, then the average gate power loss is dash. Then the average gate power loss is dash. If the question is framed like this, how to do this problem, you tell me? Then the average gate power loss is dash. Okay. Simple. Can you answer what is the solution for this problem? Yes, answer this. For DC triggering, what it is given, that average gate power loss, you know this formula, na? Vg into Ic. How much it is given? 20 watts. 20 watts. If pulse triggering is applied, 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 these are related to this topic, that's why I am giving, even though it is not given in classroom workbook, that I am giving one or two. Okay. If pulse triggering is applied, then you tell me what is the average gate power loss? What is the average gate power loss? That is this, you know, na, Vg into Ic into delta. Okay. What is Vg into Ic? 20. What the delta is given? Duty cycle is given. A duty cycle of 0.2 is applied. Then 0.2. Then how much you can get? 4 watts. Okay. See the difference. That's why, as compared to DC triggering, for the same SCR, in pulse triggering, average power loss is less. That's why I told already now, the power losses are high in the case of DC triggering. The power losses are less in the case of pulse triggering. That's why which triggering is more favorable? Pulse triggering is more favorable. Okay. Now see another example based on this concept itself, not mentioned in this workbook. Go through this. Note down that one. Okay. For example, if the question is framed like this, how to answer? Based on same concept. Question is framed like this. Okay. In a pulse triggering of SCR, 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 okay, in a pulse triggering of SCR, gate trigger voltage, gate trigger voltage, okay, gate trigger voltage is 5 volts, and gate trigger current, and gate trigger current, and gate trigger current, and gate trigger current is, okay, and gate trigger current is 10 milliampere. Gate trigger current is 10 milliamperes. For a switching frequency of 100 Hz, for a switching frequency of 100 Hz, for a switching frequency of 100 Hz, okay, for a switching frequency of 100 Hz, and non-conduction period of, and non-conduction period of, and non-conduction period of, and non-conduction period of, for a switching frequency of 100 Hz, and non-conduction period of, and non-conduction period of 5 milliseconds, then the average gate power loss is dash. Then the average gate power loss is dash. Then the average gate power loss is dash. A non-conduction period of 5 milliseconds, then the average gate power loss is dash. If the question is framed like this, how to answer? You think? Tell me. Okay. But the solution for this problem. Average gate power loss equal to PGAV equal to Vg into Ig into delta. But delta is not given. How to write? Vg into Ig equal to T on by T. Then how to write this formula? Vg into Ig into T on into F. Frequency is given, but T on is not given. But T off is given. Non-conduction period, T off is how much? Non-conduction period, T off is how much, you tell me? The non-conduction period, T off is given as 5 milliseconds. T off, non-conduction period, T off equal to 5 milliseconds. Okay, switching frequency, F equal to 1 by T na? F equal to 1 by T. Then T equal to 1 by F na? 1 by 100. 1 by 100 means this 10 power minus 2 na? This you write how many milliseconds? 10 milliseconds. So okay, 10 power minus 2, 10 into 10 power minus 1. That you write 10 milliseconds. Then we know that T equal to T on plus T off now. T equal to T on plus T off. From this one, what is T on? T on equal to T minus T off now. T is 10 milliseconds. T off is 5 milliseconds. Then what is T on? 5 milliseconds. Okay. Now, what is the average gate power loss? Now you calculate what is the average gate power loss. Yes, you tell me. The average gate power loss equal to PGAV equal to VG into IG into T on into F. Okay, average gate power loss. Then what is VG is given? Gate voltage 5 volts. What the gate current is given? 10 milliampere. Okay. What is on time we are getting? 5 milliseconds. What the frequency we are getting? 100 Hz. Okay. This is how much you get. This 110 is cancelled. We can get 25 milliwatts. Then the average gate power loss equal to how much you get? 25 milliwatts. Okay. Like this, we can solve any question based on this concept. With this classroom workbook questions based on the concept of turn-on methods, gate characteristics and switching characteristics is completed. Okay. In the next session, we will continue with the next concept in the thyristor itself, in chapter 2 itself, that is power semiconductor, corresponding to thyristor concept itself. In the thyristor concept, up to now in the thyristor I started with static VA characteristics, that is modes of operation. Then I explain about turn-on methods, that is two transistor analysis. After completing that two transistor analysis, I discussed about what is the switching characteristics. In the switching characteristics itself, I explain about turn-on characteristics and turn-off characteristics. After completing the turn-on and turn-off characteristics, I discussed about gate characteristics, and based on all these concepts, I solved these classroom workbook questions. Okay. The next important concept with respect to thyristor itself, I want to discuss protection circuit. The next concept is protection circuit of a thyristor. How we can protect the thyristor from the various abnormal operating conditions. All these concepts I will discuss in the next session. Is it clear? Okay. Okay. This about some topics. Based on this topic too, I solve these some problems.